Welcome. In this video lecture, I am going to talk about multi-item inventory models subject to certain constraints. Okay, so in this lecture, we will cover different inventory models with respect to the constraint. Could be the budget constraint, could be the space constraint, could be the number of order constraint. Okay, so one constraint at a time. Even we will also talk about if we have the multiple constraint at one go. So we will briefly talk about this one as well. So first of all, we will see how we can solve if we have a single constraint, either it's a budget constraint or either it's a space constraint or either it's a number of order constraint. Then we will see that how we can solve these model with respect to Excel. In Excel, we will talk about the two things. Either we can use goal seek approach to solve this problem, or either we can use the Excel solver to solve this problem. So let's first of all discuss that right now we are talking about the inventory model, that is the multi-item with under certain constraints. So the main objective is we need to find out the economic order quantity for every particular product. Okay, so how we can define this multi-item EOQ model with budget constraint problem? So consider we have an inventory system of n items. That means we have the multiple items, and we have a constraint that is basically the available budget constraint. Okay, so against every item we have the certain item cost, right? So how we can define this budget constraint? That is going to be the unit cost of every product multiplied by the average inventory of that particular item. Okay, because we have the n items, so that's why we are summing from J1 to n. Okay, so that means for product 1 we have the average cost, for product 2 we have the average cost, for product 3 and up to product n. So if I open this one, that can be written as C1 Q1 2 plus C2 Q2 over 2 up to Cn Qn divided by 2. This should be less than budget constraint, right? Where Q is basically representing the order size quantity. Okay, so as we know that using the basic EOQ model, how we can find out this optimum order quantity? Okay, so this is the total cost. This is basically the ordering cost. This is basically the carrying cost. Okay, so this is basically per order. This is number of orders. This is basically the carrying cost. This is basically the average inventory. So the total cost, we have the ordering plus carrying cost. Using this function, we can find out the optimum order quantity. As we know that how we can find out this one, because this total cost is the convex function. Okay, what does that mean? Basically we will differentiate this function with respect to q, and we will put it is equal to 0, and based on that we would be able to find out the value of q. And then the answer of the first differentiation is again differentiating, that is a second order derivative. Okay, and that must be greater than or equal to 0. So if the second order derivative is must be greater than or equal to 0, then we can say that against this q value, this total cost is going to produce us the minimum total cost. Okay, so that's where we can call it as the optimum order quantity. So this optimum order quantity formula can be read as square root of 2 into order cost multiplied by the demand divided by the carrying cost. And this carrying cost can be written as I into C. I is basically the interest rate or the carrying inventory rate multiplied by the unit cost. Okay, so this is basically the economic order quantity for the single product, right? So why this is important? So let me show. If I am going to talk about the multiple item EOQ model with certain constraint, right now we are talking about the budget constraint. So how we can write down, that is we want to minimize against all the products quantity. So that means we want to minimize against every product's order cost. This is basically order cost against the product J multiplied by the annual demand of the product J divided by the quantity of the product J, plus this is the carrying cost or against the product J multiplied by Qj divided by 2. So this is the total cost against all the product which we would like to minimize. Okay, subject to we have a budget constraint. Okay, so in order to solve this non-linear programming model, okay, because in the optimization language, this is basically a non-linear programming model. So how we can solve this one? So first of all, remember that whenever we are going to solve this multi-item or multi-product economic order quantity model, firstly we will ignore this constraint, okay, and we will solve the against every product using this single item economic order quantity model. Okay, so that means using this particular formula for every particular product, we are going to find out the optimum order quantity. Okay, and then we will put those answers over here. We know the unit cost against every product, okay, multiply by the optimum order quantity which we have obtained from here divided by 2, and we will be known the budget amount we have. Okay, that is the restriction we have imposed. Okay, if this constraint is satisfied, then we will say this is the optimum cost. So that means there is no need to consider in the solution that constraint, right? Okay, like as I'm mentioning over here, like, so the first way to solve this one, as I mentioned, that consider as an unconstrained problem, which means initially do not need to consider this problem. Just using this formula, find out the every product optimum order quantity, okay, and find out the total cost. If this optimum order quantity satisfy this budget constraint, then this would be our optimum solution. But if this constraint is not satisfied, then what we will do? Okay, if this constraint is violated, then we are going to rewrite this non-linear programming model, and we are going to use the Lagrangian approach. What was that? That is going to be written as this one. So this is minimizing the objective function minus lambda. Lambda is basically the Lagrangian multiplier. Okay. And then we have the budget constraint, which is B minus the left hand side. Okay. So this is basically our budget constraint. So in this function, we now have the two decision variable. If you remember, in the total cost of the single item product, what was our decision variable? That was Q. So we were interested to find out the value of Q, as we already know the ordering cost. Okay, against every order, we already know the carrying cost against every product, right? But in this equation, we have the two decision variable. One is the Qj star, so that means the optimum order quantity against every product, as well as the lambda, which we have introduced using the Lagrangian multiplier approach. Okay, so in order to find this one, we are again going to use the same approach as we have adopted against a single product. That what we are going to do is we are going to see that is this objective function is a convex function or not. Okay, so as we know that if we have a single product, what was or a single decision variable, so what was the convex property? That we are going to differentiate that particular function with respect to that particular decision variable. If we have single one, so that is should be equal to 0. Okay, and based on that we would be able to get the value of Q, as we have done with respect to uh, the single order quantity economic order quantity model. And then we will take the second order derivative of the result of the first order derivative. Okay, and then we will see that is it greater than 0. If it is greater than 0, then we will can say that that Q which we get from this equation is the optimum order quantity. But if we have the multi-item product, so again we need to check this convexity property. Okay, so for that, basically, let me show you what is that one. That is the mathematics behind that one is that we need to check the that is the this multi-item product function is a convex or not. So for that, basically we are finding the gradients and Hessian matrix. Okay, so gradient mean we are going to differentiate that function against every variable. Like right now we have the function of this one, So that means we are going to differentiate this function is against q1, q2 up to qn. So the first order derivative, and similarly against lambda. Okay, the first order derivative is called as the gradient. Okay, and then once we will get the first order derivative, again we will take the second order derivative against that first order derivative, and the second order derivative, this is going to be resultant as the Hessian matrix. Okay, so in order to know whether that multi-item product is the convex or not, so this Hessian matrix must be the positive semi-definite against all the values of x, or you can say in our case in all the values of q's and lambdas. Okay, so that is also that this positive semi-definite mean that this should be greater than or equal to 0. Okay, so that is basically the mathematics property behind that one. So right now we know that this is a convex function. Okay, we have already done, so I'm using the same approach. So first I am going to differentiate this function with respect to qj, and going to put this function is equal to 0. Okay, so once we do that, we will get this value. Okay, so we differentiate this one, we will get this one. So using this equation is equal to 0, we will get the value of the first Decian variable, which is qj. Okay, so if I simplify this one, I will get the value of qj. So this can be written as this one. Okay, so this is the q formula for, in order to the optimum order quantity. Okay, the second basically Decian variable is lambda. So how we can do that? Now we are going to differentiate this function with respect to lambda. So we will get this one, because this here we do not have the lambda, so this is going to be 0. The resulting is the same, this constraint, this is going to be 0. Okay, and we will simplify this one. Okay, now, what we are going to do is using this equation, we will find out the value of lambda. How we can do that? Simply, we are going to replace the answer of this q over here. Okay, and then we will simplify this one, and in order to get the value of lambda. So after simplification, I have get the value of this lambda, which is basically equal to 1 over 2 into the budget square. Okay, the amount we have restricted, sum j into 1 to n, the order cost of product j, demand, unit cost, square root. Okay, and then square minus carrying rate, or you can say the interest rate. Okay, okay, so remember that in order to find out the optimum order quantity, and once we have the optimum lambda, one way is that in order to find out the optimum order quantity is that we should get the value of q star as we have done over here. Okay, that is this one, and then we should also know the value of lambda using this formula. The other approach is that if you do not want to find out the value of lambda, so the other approach we can adopt is that once we have get the value of q, okay, here we do not know the value of lambda, so I can do some mathematical operations on that one. So let's say I decided that I am going to divide numerator as well as the denominator with respect to ICJ. Why I am doing that? Because I know that 2 into C naught J dj divided by ICJ is equal to basically the economic order quantity formula for single product. Okay, so that's why I decided to divide this numerator as well as the denominator with ICJ. Okay, so the upper part, so that can be written separately, and now the remaining is 1 over, so this is going to be 1 plus lambda cj icj. Okay, so now this is the qj for the multiple item. Okay, still we have the lambda. So the one way to deal this equation is that if we take a assumption of the proportionality, and what was that one? That unit cost divided by the carrying cost is remain constant for every particular product. So that means the ratio of the unit cost of the particular product and the carrying cost of that particular product. So this ratio remain constant. Okay, if that is the case, then we can rewrite this one is 1 plus lambda c is the unit cost divided by the carrying cost. The other way is we can cancel out this Cj with Cj. We will get the value of square root of 1 over 1 plus lambda I, and now I am calling this part is equal to m. Okay, if I am calling this part is equal to m, that means I need to find out the value of m because I do not know the value of lambda. Okay, so how can I find out the value of m? So simply by putting this value in the in the budget constraint. Okay, so in our multi-item budget constraint model, our constraint was this one. So I'm replacing this Q with this value, which is EOQJM, and this C by 2 is separately. Now, by simplifying this one, we will get the value of M. Okay. So, uh, so remember that in order to solve the multi-item economic order quantity with certain constraint, like in this case, we have the budget constraint, we have discussed there could be one approach is if first of all we are going to solve the question in an unconstrained model. Okay, if the constraint is satisfied, there is no need to consider the budget constraint or any other constraint, so that solution is going to be optimum. If the constraint is dissatisfied or violated, then we need to do this all the thing. So let me solve the problem and we will get the clear understanding. Okay, so we have the example of the inventory parameter for the three products. So let's say we have the three product A, B, and C. These are the three products. Okay, so the annual demand against three product we have forecasted. Okay, so that is the ordering cost against every order of that particular product. We have the unit cost. We have the inventory carrying cost. You can say the interest rate against this one. So we can find out the carrying cost by multiplying this inventory carrying rate or the interest rate 25% multiply by the unit cost. We would be able to get the carrying cost. So you can do that. That is, let's say for the product A, this is 0.25 multiplied by 50. I will get the carrying cost against the product A. Okay, and then we have we want to find out the economic lot sizing for every product, and there is a restriction of the budget that we do not spend more than $10,000. So how you can solve this problem? First of all, we are going to solve this with unconstrained problem, which means we are not considering this budget. We are going to solve every product separately by applying single product economic order quantity formula, which is this one. Okay, and we are going to find out the optimum order quantity for every product. Okay, so the formula is 2 into C naught is the ordering cost multiplied by the demand, which is this one, that is basically 10,000. Okay, that is the demand, and the ordering cost was $30 divided by, okay, we have the $50 is the unit cost multiplied by the inventory rate, which is interest rate, and based on that we are getting that the optimum order quantity for the product is 69. Same is the case for B as well as C. Now we need to check what is the total cost we are going to bear. So if we are going to calculate the total cost, that is going to be the average total cost, which is basically 1 by 2 into, which is the average. We are calculating the total cost. So Q against the particular product 1 multiplied by the unit cost. So that is the product cost, unit cost. Okay. So plus product B, that is the optimum order quantity multiplied by the unit cost, which is $100. Same is the case for the C. Okay, so if we calculate the average cost, that is basically 11,125. But the restriction was that it shouldn't be greater than $10,000. Okay, so which means the constraint is violated, which means the budget constraint is violated. We need to um, take up that budget constraint, which means we need to apply that Lagrangian optimization approach. So for that, we already have find out the value of QJ. Okay, that is um, that is this one. Let me show you again. Okay, that is this one. Okay, so this is the optimum order quantity. We have already find out the lambda value. Okay, one approach is, so that is, which is basically the method number one. Okay, so using this formula, we have put the value. So which is 2 into ordering cost. That is $30 multiply by annual demand is for product A is 100,000. Then we have CJ, which is basically the unit cost, $50 into I is the inventory rate or the interest rate, which is 0.25 plus lambda. Okay, so how you can get the lambda using this particular formula. Okay, so the value of lambda is 0.058. So multiply by 0.058. So under the budget constraint, the optimum order quantity is not 69 but 62. Same is the case for product B. Same is the case for product C. So if we get this, the total average cost, which is $10,000. Okay. Now the budget constraint is satisfied. So this is the method number one, method approach number one. So second approach is, instead of, let's say we are not computing the value of the lambda using this formula, we have already computed the value of Qj, and then we are going to use this M approach. That is the method number two, in order to find out the optimum order quantity. Okay, so how you can do that? Again, we have find out the optimum order quantity for the single product, and we have seen that this is violating the budget constraint. Now we know this equation that Qj is going to be the economic order quantity without the budget. Okay, that is basically economic order quantity for product J, okay, into M. Okay, and based on that we have M is equal to B over 1 over 2 into this one. So this is basically the average cost. Okay, that is basically the objective function cost. So the budget was 10,000 and this was basically 11,000. That is basically this one. Okay, that is this one. So M is equal to 0.89. So what we are going to do is we are going to multiply by this M with every product's EOQ. So 69 multiply by this M, we will get 62. 65 multiply by M, we will get 58. 60, 82 multiply by this M, we will get 74. Okay, and based on that, again we are getting the 10,000. So either you can use the method 1 approach or either you can use the method 2 approach. So in the rest of the lectures, I will mainly focusing on the method 2. Either we are using the space constraint or any other. Let me show you if we have a space constraint. Okay, so I hope you got the idea regarding the budget constraint. So in a space constraint, again, we have the total cost that is the same. But instead of the budget constraint, now we are seeing that we have a space constraint using the same idea. This is the maximum space availability. This is the space utilized by the gth product. Okay, this is the average inventory we are storing in the store of that particular product. Okay, so using this equation, we can adopt the same approach. Okay, we can apply the Lagrangian optimization. Again, in order to find out the value of lambda and value of Qj, we differentiate this function with Qj and we will get the value of Qj. And then with respect to lambda, we will get this one. Now, again, using the same approach, you can find out the value of lambda. Okay, so do it by yourself. But right now I'm going to use the second method, in which I'm not going to find out the value of lambda, but I'm going to use that M approach. Okay, so we know that the value of Qj, again I am going to dividing numerator and denominator with ICJ again. Okay, and we know that this is basically the single product's economic order quantity. So this is going to be equal to M. Okay, so again this equation can be put into the constraint. Okay, so in Qj we can put this value. Okay, and then by after simplifying we will get the value of M. So let me show the example. Suppose that we are saying that determining the optimum and flexible order quantity for the two products. The products are X and Y, and the space restriction is we have the 40,000 cubic feet space available. Okay, so the annual demand is given, the ordering cost is given against every product, unit cost is given, carrying cost rate, which means the interest rate or the inventory carrying rate is given. Okay, and the space required for every product is given. Again, in order to solve this problem, first of all, we are going to solve the problem without the constraint. Okay, by relaxing the space constraint. So that's why I'm applying the single item economic order quantity formula. So based on that, I got the value of economic order quantity for X as well Y. So the formula is 2 into the ordering cost for X is this one. The demand for that is, this is the demand, this is the ordering cost. Okay. Divided by 0.25 multiplied by the unit cost. This is X, this is Q. Now in order to see, because the restriction was the space, okay, so we are going to apply the sum of space we are going to use. So that is basic the constraint we have, that is space utilized by product J into the average quantity we have. Okay, so 1 by 2 into Sj is, that is 50 cubic, multiplied with the Qj of X is 490. Similarly, this is the 125 cubic feet for the product Y multiplied by the economic order quantity. And as you can see that the average space required based on these optimum order quantity is much more compared to the available space. So what we can do again, now we have to consider that restriction. So I'm going to use this M approach. So we are going to compute the value of M. So as we have found out the value of M is equal to this one. So this is basically, so this 2 is going to be multiplied by over here. So that's why 40,000 is the space multiplied by this 2 over here divided by, so this total cost. Okay, that is this one, right? So the value of M is equal to this one. Now this multiplied by this, we will get the with budget constraint QX. Similarly, this QY is equal to this one. Okay. Now, if we put this value into our budget restriction, okay, total space required. Again, if we calculate this one, this is 40,000 025 cubic square feet. Still, it is violating the available space. So now we need to find out the value of lambda. So that means uh, uh, based on this, we still violating this issue. So now how you can find out the value of lambda, that is with the help of these queues. Okay, that would be the much simpler way. Okay, how you can do that? So this is the qx, this is the qy we are going to use, and then we are going to apply this optimum order quantity formula of this one. Okay, so that is basically we have the new Q1, QX is 341 and QY is 4504. Okay, by putting these values over here, so QX is 341 and these value we know we need to find out the value of lambda. So after simplifying, the lambda x is equal to 0.53, and after putting the value of y's data, we are getting the lambda y is equal to 0.17. Now, the question is, should we use 0.53 lambda or should we use 0.17? So basically, these are the limits of the lambdas. So this is a lower limit. The smaller value is the lower limit. The larger value is the upper limit. So that means the optimum lambda can be in between those limits. Okay. So that means we are going to use manually hit and trial approach. So if I'm going to use lambda this one, okay, what would be the qx qy and what would be the total cost? So the available space is 40,000, so this is basically 30,000 this one. If I'm using lambda this one, okay, if I'm using lambda this one, no, this is violating. If I'm using lambdas this one 0.21, still we are violating. If I'm using lambda this one, now we are almost fitting the cubic space. But this is quite tedious work if you are going to find out the value of lambda manually. So is there any way that we can exactly find out the value of lambda if we are facing this particular issue? Yes. So for that we can use basically the goal seek approach in the Excel. Okay. So what was that basically? So let me show you in Excel. Okay, so in Excel, what I have done, I have just write down, put the data that was given in our problem. So basically the annual demand of product X, annual demand of product Y, ordering cost, unit cost, okay, carrying cost, as well as the space. Then what I have done is I have just simply applied the EOQ formula of the single product. Okay, the formula I am going to use is basically the round off. Okay, a round off up to 0, which means I do not need the fractional part of the result. Okay, so I'm saying square root of 2 into C4 is basically the order cost. That is the single item economic order quantity formula, multiplied by the annual demand divided by unit cost multiplied by carrying rate. Okay, so I'm finding the economic order quantity, optimum order quantity without the space constraint for product X. Same is the case for product Y. Okay, and then that is now we are calculating the total space required. So how you can do that? Simply multiplying this space required of the 1 unit of X multiplied by the uh, quantity we have. Okay, that is this one. That similarly we have this one. So if we simply sum of this one, that we will get this, because we need to find out the average space if you remember the restriction. So that's why I'm dividing by 2. So that's why the total space is going to be this one. We are going to not considering that space constraint. Now, in order to apply the goal seek, again I am going to apply this formula, economic order quantity, with space constraint formula. Okay, that is basically this one. Okay, which is 2 into C naught into dj over I into Cj plus lambda into Sj. That is again square root 2 into basically that is basically the ordering cost multiplied by the annual demand divided by this C6 is basically the carrying cost multiplied by the carrying rate. Okay, plus we have the this E15 is basically the value of the lambda which we are going to compute with the help of this goal seek approach, multiplied by the Sj, which is basically we are mentioning over here. Okay, which is basically the unit cost. Okay. Okay, so sorry, not the unit cost, but the space required. Okay, this lambda and multiply by this one. So same is the case for y. Now these values we need to find out. Okay, these, and over here we have applied the formula of the total cost, that is basically is going to be equal to this C15 multiplied by this 50. Okay, this is basically we are adjusting this quantity. So this multiplied by this, so and this multiplied by this, and then divided by 2, which is the total space required. So the actual issue is we need to find out this value of lambda. Okay, which were using over here hit and trial approach. So how you can do that? Simply go to the in Excel data tab. We have what if analysis. Go to goal seek. Okay, in a set cell, that it should be the total space. Okay, and then two value, which means this value should not be more than 40,000. Okay, and changing cell mean the decision variable, which is the value of this lambda. Okay, press OK. So now after solving this one, now it is giving us 2.2112. Okay, so that is the value which we can use over here in order to find out the EOQ. And now it is giving us the Q1 X value is similarly QY value, as well as the space constraint is also satisfied. I hope you got the idea regarding how you can uh, solve this multi-item problem using the Excel by finding the value of lambda. So this is the optimum order quantity for product X. This is the optimum quantity for product Y, as well as the space constraint is also satisfied. Okay, so there is another approach that we can use the Excel solver. Okay, so in Excel solver, what we are going to do is that first of all, we have again just entered the required data. Okay, and then after entering the data, I have computed the carrying cost. How we can do the carrying, calculate the carrying cost, that is carrying rate, which is the interest rate multiplied by the unit cost. So we will get the carrying cost against product X, same as the against for product Y, which is 0.25 multiplied by 80. Okay, that is going to be the carrying cost for product Y. And then these two values we need to find out. Okay, so these are the decision variables, so these are the empty values, so you can simply mention 0. Okay. And then what we are going to do is we need to find out these terminologies. In order to find out the carrying cost, we need the average inventory of product X as well as product Y. Similarly, the number of orders, that is number of orders, the formula is the annual demand divided by the optimum order quantity. So the demand over the optimum order quantity, we are getting this one. Okay. Same is, so that is the basically C3, which is the demand of product X, divided by C12, which is basically this optimum order quantity. Similarly, this is going to be this 15,000 divided by the value of this one. Over here, we would be able to get the number of orders. So this is the average inventory. Using this, we would be able to get the carrying cost of every product. Using this, we would be able to get the total ordering cost. So in order to calculate the carrying cost, we are saying that this should be equal to this carrying cost, which we have already calculated per unit carrying cost. So in order to calculate the ordering cost, this is already given. This is this one. So that's why we have simply written down equal to this one. Okay. In order to calculate the total cost, so this is going to be equals some product. So this should be multiplied by this. This should be multiplied by this. This should be multiplied by this. This should be multiplied by this, and then sum. So for that, we are using the sum product formula. Okay. So the selection of this and then comma selection of this one. Okay. So let me write, which is basically equal sum product. Okay. And then we will say this should be multiplied by and sum with this one. Okay. And then after that, we are basically mentioning the space requirement for product X. The space requirement for product X is we are saying that this should be equal to this one. This is should be equal to this one. And over here, we are going to apply the formula that the total space we are utilizing. So again, for that, we are going to use is equal sum product. So this should be multiplied by multiplied with the C basically 15, which is basically the average inventory we have of those products. Okay. And this is the restriction that this should be less than or equal to this one. Okay. So after applying, so this should be empty. After applying these formulas, now we are going to go to data and then we are going to click solver. Okay, over here the set objective is basically the objective function value, that is the total cost, and we want to minimize it. The changing cell is basically our decision variable, that is this one, qx and qy, and we have the constraint. Okay, and the constraint is basically that this should be, okay, okay, let me delete this one first of all. So we are saying this should be less than or equal to, right now I am merely further restricting it, this should be equal to what? This should be equal to this one. Okay, and press OK. And because this is a nonlinear programming problem, so for the solution method, we have to use this GRG nonlinear and make sure this is selected and press solve. Okay, and press OK. Okay, let me check this one again. Okay, now we are getting this one. So earlier it was written, so write down 1 1. Okay, because due to that one we are getting the error. Okay, but right now we get the answer. So you can see that the constraint is satisfied. The optimum order quantity of X is 410.76. The optimum order quantity 475. These are the same answers which we have get using the goal seek, as you can see over here as well. Okay, so either you can use the goal seek approach or either you can use the Excel solver approach. Okay, so let me do another thing, that let's say right now these values are in a fraction part. We want that it should be in an integer. So we are further restricting it. Okay, that is basically we are applying not the mix non-linear programming, but non-linear integer programming. So that means we are further adding another constraint that these two variables must be integer. Okay, So press OK, and again, if we are solving it, press OK. Now we are getting the integer solution. Okay, so I hope you got the idea regarding if we have the um, multi-item EOQ model with single restriction problem. Now let's see. So this was the without. You can say that uh, this solution was. Let me do this one. Okay, so this was without integers, so this was with integer restriction. So I have solved. Now let's say if we have the constraint of number of orders. Okay, so again the objective function was the total cost subject to, this is basically the number of orders formula, that is divide demand divided by the economic order quantity of that product must be less than the number of orders. So again you can find out the optimum same using the same logic to find out qj as well as lambda. Okay, so this you can do by yourself. Now if we have the multiple constraint, okay, so first of all, the main thing is if the constraints are both in the same direction, which means like if we have the constraint of budget as well as the space, in both cases we would like to reduce the quantity size. Okay, in that case what we are going to do is we are going to solve unconstrained. If both the constraints separately satisfied, we will say this is the optimum. Then you can take first constraint. Okay, if the first constraint is satisfied, then again check the second constraint. Okay, so remember that the constraint in a problem are not opposing each other. As I am giving the example, both are basically indicating the same direction. Okay, like the budget as well as the space constraint, both want to reduce the EOQ. Okay, but if we have a conflicting constraint, okay, we have two or more than two constraints but they are conflicting, like we have a budget and the number of orders. In a budget constraint we will try to attempt to reduce the EOQ. Okay, but in a number of orders, however our ordering cost should be reduced, we will try to increase the lot size. Here we have a problem, we cannot adopt this approach. Okay, so for that you can use Excel solver. Okay, simply so that is basically a non-linear programming approach. Same is the case if we have a space constraint and the number of order constraint. Same over here, in a space constraint we will try to reduce the lot size, but in the number of order we will try to increase the lot size. Again we have a conflicting, so in that case both the constraint must be satisfied, or there is another solution approach is try to pick the more important one in that particular situation. Okay, so this is your assignment. This is where we have the multiple constraint. Okay, we have the you can say the average ordering cost, mean entry cost, as well as we have the space restriction, and this is the data. So you can use Excel solver to solve it. Okay, so thank you so much. See you in the next lecture.